Okay, so we are on to kinetic energy now. So kinetic energy is opposite of potential energy. Kinetic energy is based on motion, where potential energy is based on its position and height. So we've already kind of talked about, just looking at that roller coaster situation, that it kind of results from the work or the change in the potential energy. And so since kinetic energy has to do with motion, it involves velocity. So here's your equation for kinetic energy. So it's 1/2 mass times velocity squared. And people always forget that squared right there. And you can't, or it'll mess up your whole answer. So since speed is squared, if you double the speed, then it increases it by 4. Okay, so mass is important, but in kinetic energy, but velocity is really important. All right, so we're gonna have to go over to our notes again, and we can do an example for our kinetic energy here. So we've got example 3.7, and this is saying that a 7-kilogram bowling ball is moving in a bowling lane with a velocity of 5 meters per second. What's its kinetic energy? All right, so a 7-kilogram bowling ball is moving at 5 meters per second. What is its kinetic energy? All right, so we've got mass and we've got velocity. So kinetic energy is 1/2 mass times velocity squared. So 1/2 times 7 times 5 meters per second squared. So that's going to give you about 87.5 joules. Okay. Whenever you go to do the math on this, just remember your order of operations. And that exponent there means you need to do it first. So if I were you, I would type in 5 squared on my calculator times 7 times 1/2, and that should make you good, you know. Like I said before on a video, that I always have problems with from students is just calculator issues. Okay, so this one is, this example 3.8 is saying, let's see, we've got a 100-kilogram football player going at a velocity of 6 meters per second, and it wants to know how much work was done. Okay, remember how I said work and potential energy was interchangeable? Well, it is with kinetic energy too. Okay, so whenever it says work, you can still just use kinetic energy. If something is moving, see how it says the football player is moving with a velocity, then you're going to want to use kinetic energy. All right, so we've got 1/2 times 100. That looks like 1,000. That's not what I wanted. 100. Got to put that decimal in there. Velocity 6 meters per second squared. Whenever you do that, you should get 1,800 joules. Remember your significant figures, so that 6.0 has 2 significant figures, so that's why you have to have that 1,800, you know, with no other numbers besides 0 behind it, okay? I do want to kind of, I think that there is actually an example coming up that does this. Let me see. As it talks about energy flow, possibly. Yes, it does. So I will wait to mention that till we've gotten through energy flow. Okay, so energy flow. Energy can do work as work against inertia. So inertia, remember, kind of deals with mass. Remember, it's wanting to stay at rest, or it wants to stay in motion unless acted upon by an unbalanced force. Well, this person trying to push this Volkswagen is obviously an unbalanced force. So it's working against inertia. The second picture is working against gravity, and you're picking up a box, against gravity. That's why you can feel its weight. Friction. So depending on the material, if you're trying to push something across carpet versus trying to push it across an ice skating rink, you're going to obviously experience different friction there. And then the shape of whatever the object is can cause you to have a different work. So this one's showing you like the shape of the spring. We didn't really talk about springs too much, but if you think about like a rubber band, and if you pull a rubber band back, it's going to have some potential energy, right? Because as soon as you let go of that rubber band, it's going to go flying through the air. So kind of like a spring. And so the different shapes of springs, some springs are very rigid, where some of them are, really easy to pull. So it just depends on the shape. And then of course you can work against a combination of all of this stuff. All right, so okay, energy forms. These you do need to know. Okay, so you've got mechanical energy, which is like your kinetic plus potential energy, which we get back into here in a minute. Sorry. You've got electrical energy, which is like your charges and currents. Chemical energy, which involves chemical reactions, which we'll do whenever we get into the chemistry section of our book. By the way, everybody always loves the chemistry section more than the physics section, so something to look forward to. Radiant energy, this is like our electromagnetic scale, which we kind of will go through here in another video. And then nuclear energy, which involves, the nucleus of atoms, and then, of course, nuclear reactions between those two. So this is the one that I kind of want to get to, because this is showing sort of a conversion between potential energy to kinetic energy and vice versa, which I kind of already talked about whenever we did the roller coaster. This is showing you a pendulum. So think of a ball on a string that's going back and forth, or a Newton cradle, or even this guy that's bowling, okay? So it's going from one form to another. And you add up the kinetic and the potential energy, and you can get the total energy. So energy conservation. I just want you to know that we talked about this at the beginning, but that energy is going to be the same through the whole system. So the potential energy added to the kinetic energy should be what it was from the very beginning. So you can actually set those two things up to each other. So you can set up potential energy equal to kinetic energy, okay? And then they just are plugging those equations for, like, potential energy's equation is mass times gravity times height. Kinetic energy's equation is 1/2 mass times velocity squared. And then they're saying that you could solve for, something other than energy. You could solve for, say, like velocity. So we're going to do that math really quick. I'm going to kind of do it down here a little bit. So mass times gravity times height is equal to 1/2 mass times velocity squared. Let's say that we wanted to figure out what the velocity was at a certain height of the pendulum. So here's our pendulum right here. And let's say that I wanted to find out what the velocity was at that height right there, okay, as it's swinging down. So you can take and you can rearrange this. Algebraically, this might look a little bit harder than what we've done so far. So what I always say is, if you've got a half right here, you can divide by a half to the other side. Okay, that's totally fine. Or you can multiply by 2 to the other side. it's going to give you the same result. I always multiply by 2, but you can do the divided by a half if you like that better. All right, and so I'm just going to write out what we have so far. So we have 2 times mass times gravity times height is equal to mass times velocity squared. I got rid of that 1/2 by multiplying it by 2. And then I'm going to divide by mass. Well, what happens to the mass over here now? It's going to cancel. Okay, so I'm left with 2 times gravity times height is equal to velocity squared. Okay, now how do I get velocity to not be squared? I have to do the square root. Okay, so velocity is equal to the square root of 2 times gravity times height. Okay, and that is how you could find the velocity. So there's a little bit more going on there, but you could find the velocity at a certain height. Like it's giving you this example at 10 meters, the potential energy was 98 joules, and it hadn't been released yet, so it wasn't moving, so it had 0 kinetic energy, and the velocity at the time was 0. But if you release it, right, then it's moving, and it's at a height now of 5, so that changed the potential energy by half, and then you could use this equation right here to find the velocity. All right, so you just do the square root of 2 times gravity times that 5 meters. And then the kinetic energy, you of course could just do your 1/2 mass times velocity squared. So once you find the velocity, then you'd be able to find that kinetic energy. And you can see that I want to point out that 49 joules plus 49 joules is going to equal 98 joules. So that goes back to this concept of potential energy and kinetic energy are equal to each other. Okay? And then at 0, like right before it hits the ground, it's going to have basically 0 potential energy, and then the velocity is at its fastest because it's, got mostly kinetic energy or all kinetic energy at that point. So it's got 0 potential and then 98 joules of kinetic. So that energy has been conserved through the whole entire process. Okay. I'm going to stop the video there if I can get to